I'm very pleased to introduce the first speaker, Amir, who's going to be giving the MIP talk on Yin-Yang, concealing the deep embedding of DSLs. Please go right ahead.
Yeah. Thank you so much for the introduction. Yeah, you can. Thank you so much for the introduction. This is Amir. My family name is Shaikhha, if it's a bit hard to pronounce. And so this paper was originally presented 10 years ago. And so it's joint work with Vojin, Jovanovic, Sandro, Stucki, Vladimir, Nikolaev, Christoph, Koch, and Martin Odersky. And so just as a quiz at the beginning of the talk, I want you to find 4 differences between the title that I had and what was used 10 years ago. Can you spot anything? Perhaps they are the same or not. So let's see them. So the first difference is that, of course, I'm presenting rather than Vojin. The second difference is the affiliations have changed, a lot of them. I think except Christoph and Martin, who were faculty members, everybody else is in some other place. By the way, I'm at the University of Edinburgh. The third thing, yeah?
You added a colon behind Yin-Yang?
Yeah, okay, then 5 differences. Yeah. So the EPFL logo has changed a bit. Yeah, they made it look like more like MIT, basically. That's what they want to do at EPFL. And the third one, which is the fifth one, which is basically a bit implicit, is that the Scala version has changed. You cannot see it there, but back then it was Scala 2, and nowadays we have Scala 3. So they're not actually the same. But that being said, let's see actually what this paper was about and how it changed everything from then in the last, basically. Oh, by the way, there is another difference, which you cannot see here, but that slide 10 years ago was prepared with a library called Reveal.js. I don't know whether it exists nowadays or not, but I decided to recreate it with PowerPoint. So let's start basically by giving definition for each of these terms. So it's a DSL session. Let's first define what are domain-specific languages. So as the name suggests, they are languages for particular domains where they allow us to basically exploit the domain knowledge, and perhaps in the domain we have some sort of algebraic structure, some sort of algorithmic knowledge, and specialized data structures. And we could have basically domain-specific languages which are very high level, or we could have ones which are very low level. Let's give some examples for the domain-specific languages. So some of the familiar ones these days in the AI data science age are basically Apache Spark, or SQL, or poor person's SQL, which is basically Panda data frame, or TensorFlow and PyTorch. All of these, they don't look like DSLs, but they are actually DSLs. And there are some differences between a domain-specific language like SQL and a domain-specific language like PyTorch and TensorFlow. So in terms of techniques that we use to implement them, they are different. So we have either external DSLs or embedded DSLs or internal DSLs. And then whenever we have embedded DSLs, we have shallow or deeply embedded versions. So external DSL, one great example of it is basically SQL, which means that we have to develop the full-fledged pipeline, compilation pipeline for that language. And for example, relational databases are the implementations for them. And I would say the other very successful example is Excel, the formula that you use inside Excel, that's also a domain-specific language. It's an external one. But what are embedded domain-specific languages? They're basically languages that are reusing. They're like parasites. They are basically reusing the front end of the host language compiler. Rather than you building the parser or the type checker for your language, you can basically reuse the one for another language. And the first time that it was introduced was basically by this seminal paper by Paul Hudak, where basically they have advocated for, rather than building the entire pipeline, let's define it as kind of a library inside another language. And this way, throughout the time, we can basically amortize the cost that it will take to build that language with respect to the maintenance cost. So the title of the paper had something like deep embedding. Let's see what we mean by deep embedding. Before that, let's see what is the opposite of deep, which is a shallow embedding. So the shallow embedding means that for whenever we want to embed a language inside a host language, we have to represent the values of that embedded language. So in the shallowly embedded versions, the values in the embedded language are directly represented by values inside the host language. And so this talk is going to focus more on the Scala programming language. What is the best example of a shallowly embedded DSL inside the standard library of Scala? Who has a guess? I'm going to reveal it. Scala collections. Basically, as a type, you have something like a collection, a list, or a sequence in this case. Then you have a bunch of constructs, operators on top of the list, like zip, map, all these kind of things. And the cool thing is that it's going to make it much, much easier to write programs. If you see some of the good, nicely written open source implementations of libraries on top of Scala, you see that they greatly use the Scala collections. But there is a tiny, more than tiny, a bit of issue with actually these shallowly embedded DSLs, which is basically there is this abstraction overhead that is associated with basically just using the host language to represent everything. So there is something that compilers should do, especially whenever we have a domain-specific language. We can leverage the knowledge that we have, the algorithmic knowledge, the domain knowledge there. So for example, in the case of lists, we know that, okay, it's a zip followed by a map. Each of them has a loop inside them. Perhaps we can do loop fusion. And to do that, we cannot rely normally on the compiler of the host language to do that for us. Why? Because the host language compiler, it's doing basically something generic purpose. It doesn't have the domain knowledge. We need to teach the compiler how to do that. And this is what deep embedding is for. So rather than representing the values directly inside the host language, we can represent it symbolically and then rewrite the symbolic representation by leveraging the algebraic knowledge. So we have seen a very nice example of a shallowly embedded DSL. This, a little bit more messy version, is actually something that corresponds to the deeply embedded version. So here you can see that basically I'm representing symbolically a minus operator, or basically a constant value. And then, in order to write a program, I have to do some sort of annotations, basically to hack the type system of the language to say that it's a symbolic representation. That's what these rep types are standing for. So you see that we are saying that, oh, y is a representation of an integer, and then we are giving it a constant value. Then the type system of the host language has some tricks to basically implicitly convert it basically to a symbolic representation. But this is very good in terms of performance. But because of all these kind of nasty type systems tricks that we are using, it's going to cause a lot of trouble whenever we are debugging the application's code. And also, in some cases, we are going to get some cryptic error messages. So just to summarize, we have basically shallow embedding of domain-specific languages, and we have deep embedding. In terms of user-friendliness, shallow embedding is really nice. It gives us very nice kind of debugging facilities. But in terms of performance, it sucks. So deeply embedded versions, in terms of performance, they're very good. But for user-friendliness, it's going to be a bit nasty. And the main insight behind the Yin-Yang framework was that can we combine the benefit of both worlds? So it was based on the realization that we have basically a development time and a deployment time. So whenever we are in the development time, we care more about user-friendliness, debugging, and these kind of things, which means shallow embedding. But whenever we are in production time or deployment time, this is where we care more about performance. And this is when we are going to need deep embedding. And what the Yin-Yang framework provided was basically some sort of infrastructure to automatically translate the friendly shallow embedding to basically the fast deep embedding before basically doing the deployment. So this is the kind of very high level view of that. Let's dig in a bit what was happening behind the scenes. So we basically have a bunch of translations. So I said automatic translation. Let's see what is the translation that is happening there. One of them is basically the so-called language virtualization that I'm going to basically give some examples of it. So for example, in the host language, you have looping constructs, and you want to basically lift that looping construct into a looping construct in your domain-specific language. Or you have a conditionals, like if then else, and you want to kind of turn them into conditions in your language. And there are certain things to basically, whenever you are doing the deep embedding, you want to basically translate the types or the operations or the constant values in the host language into the corresponding forms in your deep embedding. And the tool back then that was very newly introduced was Scala 2 macros. And this is what the tool that the Yin-Yang framework has used. So let's see the language virtualization. So basically there was a fork of Scala compiler called Scala Virtualized that was introduced basically to allow you to turn some of the key constructs, some of the keywords in the Scala language into method calls. And what Yin-Yang did was that it just used Scala macros to achieve the same thing. In a way, there was no more need to basically have a fork of Scala compiler that takes care of that. And so for examples of that is if then else or while loops. So if you were writing a while loop in your program, it was turned into a function call, which was basically this __y. And then for your domain-specific language, you could override the meaning of that function invocation. You could say that rather than basically doing a loop, construct a symbolic representation of a loop. And then you write down one interpreter or one compiler for it. Say that, oh, whenever you see this a symbolic representation of a while loop, generate like a while construct in C++, or generate a recursive function in a function language. And the same thing for some of the object methods that are provided in the JVM world. So for example, to compute the hash code, the hash function associated with every object. So these are also things that you can override them, but you cannot override them to give them a symbolic representation. So for example, if you see the way that you override hash code in Java is that you can override it to basically return whatever integer you want, but you cannot say that, oh, create a symbolic representation of an integer. But by translating it to this kind of function calls, rather than this fixed function calls provided by the JVM, you could basically do whatever you want with them. So the other component was the DSL intrinsification. That's a very hard name for me to pronounce. But this one was in particular used for the main framework, main multi-staging framework back then, which is still being used. So actually there is a talk, I think 2 talks after me, which is basically talking about the, an implementation of a DSL using the lightweight modular staging, or the LMS framework. And basically the main insight in that framework is that you provide the mirror version of all the objects that you have in the shallowly embedded world in the symbolic representation. So basically, you give a kind of meaning for this underscore underscore if, that it would basically generate a symbolic representation of the conditional. And this is going to be a bit involved, and the Yin-Yang framework using the Scala macros provides some of these non-straightforward translations. But apart from that, it also provides type translations as well. So as I said, in the shallowly embedded version, every value is directly represented as a value in the host language. But whenever we are in the deeply embedded world, we basically want to have a symbolic representation of each of the types. So the Yin-Yang framework provides a type translation. So whenever it sees a type T, it's going to convert it into a representation of T. But there are certain translation rules. So for example, now what if I have a list of T? What should I do? For example, if I have a list of integer, should I convert it to rep of list of integer or rep of list of rep of integer? How should we do these kind of translations? So these are basically some type translation rules that are provided by the Yin-Yang framework. And the DSL developer could basically modify them based on their needs. And in particular, actually, one of the interesting cases is whenever you have a function object. Let's say I have a function from type T1 to type T2. How should I have a symbolic representation of that? Should I present it as a rep of T1 to T2? Or should I present it as rep of T1 to rep of T2? So the difference between these two representations is that the second one guarantees inlining, which means that whenever there is a function that we are lifting, it's going to be inlined for sure. There is a guarantee by the type system that it's definitely going to be inlined. And this was actually one of the merits of the multi-stage programming, which was basically doing manual partial evaluation. By specifying the types, or by specifying the kind of, through the binding analysis, we actually specify where we want the functions to be inlined and where not to be inlined. So apart from the translations, it was giving some features to basically restrict the domain-specific language, meaning that let's consider a DSL for querying against a database. So let's say the user decides to put a print line there. And one thing that the framework can do is to basically report error messages that print line is not supported in this domain-specific language. So domain-specific languages do have a vocabulary inside them. You cannot do whatever you want inside them. So most of them are actually not Turing complete even. So up to now, what I've shown you was basically on the application side that the Yin-Yang framework was making it very easy for the DSL users. There was a DSL developed. I was writing an application. The Yin-Yang framework could basically just translate the application into the deeply embedded version by providing nice error messages and so on. So, but how about the developer for the DSL? So one nice thing that the Yin-Yang framework provided was that it could also, for the DSL developer, provide the kind of boilerplate code that the DSL developer had to write for basically the LMS framework back then. So here I'm emitting the code. This would have been a very awkward code that you don't want to read. And here you can see that it's really boilerplate. And basically the evaluations that we had back then was that for some of these DSLs that was used in the Delight framework on top of LMS, you could see that basically we would get like around 5 times or 6 times improvement over basically the version that the DSL developers were doing on top of Delight. And also it's competitive also to the Forge framework that the Delight developers have developed, but it was providing a DSL to write DSLs, which was even a further barrier on them. And apart from that, we have also used it for the Slick framework, which was used actually in industry for language integrated queries. And apart from that, then later on, the translations that I've shown you on top of Yin-Yang was used actually behind the scenes in the Squid framework that was published in GPCE24 and won the Best Paper Award back then. And apart from that, we basically extended the Yin-Yang framework for DSL developers to basically use some other backends apart from the LMS framework. There was basically another compilation framework that we developed at EPFL, and we basically have shown that we could basically use the same machinery to generate the boilerplate code that the DSL developers were using. And basically, we have, for example, annotated the standard library, and it was generating this massive thing that behind the scenes the deep embedding was using. So we did it actually for a query compiler in an analytical database system that was published in Database Venues, as well as the Journal of Functional Programming. We have implemented a query engine purely in Scala, and the compiler framework was generating a specialized query in low-level C code. And so the basic infrastructure was that the database developer was writing the query engine inside Scala as an interpreter, and then the database user was writing it as a query, and then the Yin-Yang framework was generating the compiled version of that, which was passed then to the systems compiler framework. And what we had seen back then was that for example, the integer standard library, it was like 12 times reduction in the code of the corresponding deep embedded version. And in total, we had like 6 times reduction in the lines of code. And of course, the performance was also very good. So to summarize, I have shown you the Yin-Yang framework, which was combining the benefits of both worlds of shallow embedding for user friendliness and deep embedding for the performance, which was allowing the programming DSLs easier for both DSL users and DSL developers. And it has been successfully used for several DSL and DSL compilers. Thank you very much.
Thank you very much. Do we have questions? I'll kickstart questions. So is there anything specific in this approach that really depends on Scala?
That's a very good question. I would say that if your language has basically some sort of facility for source-to-source translation, you could basically use the ideas inside the framework. So one particular thing is that it was the type translation process was making some assumptions about like implicit conversion and some of these features provided by the Scala language. But for example, the features like the language virtualization is something that you could use in other languages. Basically, if you see Python frameworks, I don't know who has seen a framework like Numba, which is basically a JIT version of NumPy framework. So if you see, you can basically annotate the methods with @ number, and then behind the scenes, it basically translates ASDs in a form that later on will be translated to LLVM. Basically, I would say that behind the scenes, the methodology is very similar to what Yin-Yang is doing. Rather than using Scala macros, it uses, I believe, a module called AST module that basically is responsible for turning the symbolic representation from the kind of normal Python function calls into a version which basically is a symbolic representation. Yeah.
Thank you.
Yeah.
Any questions yet? Yes? Check.
Hello, testing.
Yeah.
Good. Okay. Hi, my name's Eloise. Great talk. I just wanted to ask if you could talk a little bit more about the two different kinds of conversions of like function types into the representation types, and how one of them guaranteed like inlining and the other one, maybe gave some kind of other benefit.
Yeah. So basically, let me go back to the type translation slide. Where is my cursor? Yeah. So let's consider this version. So you have a type T1 to T2, let's say integer to integer, and basically you translate it to a symbolic representation of a function that basically turns an integer to an integer. So this version, it depends on the DSL developer of how, whenever I apply that expression to another expression, should it do the inlining, or should it just represent it's an application? It doesn't naturally do the beta reduction. However, the second form, it's basically a function in the host language. So whenever I do the application, whenever I apply it to a symbolic representation of rep of T1 or rep of integer, it will return a rep of integer. That means that it's going to return basically the symbolic representation of the output. So this kind of guarantees that the inlining is going to happen during the staging time, or during the time that I'm basically constructing the symbolic representation.
Would you say there are any particular benefits to the generic approach, as you called it? Maybe it doesn't have the inlining, but it has something else?
Yeah, I would say that the generic approach gives you more flexibility, basically to decide when to do inlining and when not to do it. So, but on the other hand, the eager approach is basically kind of doing the inlining for you. So inlining usually is considered as an enabling transformation, meaning that there are some optimization opportunities that you don't see unless you do the inlining. So for example, you have a function, you as the input pass some constant input parameters. Then if you do the inlining, you see that in the body of that, you were multiplying that constant with some other constant, let's say. Then you can do constant folding. So all the benefits that you see normally with inlining, the eager inlining approach is going to enable that for you. But on the other hand, it's going to make the code also explode in some cases, which means that you have to be slightly careful that, for example, you do common sub-expression elimination and this kind of thing so that you keep the code also in a managed size. Yeah.
Thanks very much for the questions.
Yeah.
We'll have to move along to the next speaker, so
Yeah,
let's
sure.
thank Amir. Thank you.